Okay, listen carefully, because what I'm about to tell you changes everything we thought we understood about interstellar object 3I Atlas as it rushes toward its December 19th closest approach to Earth. The anomalies keep coming. We are not crossing items off the list. We are not narrowing down the mystery. We are expanding it. Every new piece of data, every fresh observation, every analysis that gets published reveals another layer of strangeness that compounds the questions rather than resolving them. And today, right now, we have just discovered anomaly number 16. Let me be absolutely clear about what that number means. 16 separate, independently confirmed observational features that deviate from what we expect based on standard cometary physics, and based on our understanding of how natural bodies should behave when they fall through stellar systems after millions of years travelling through interstellar space. 16 data points that each individually strain natural explanations, and that collectively create a pattern so bizarre, so statistically improbable, that we are being forced to question fundamental assumptions about what we are looking at. Before we dive into the specifics of this newest anomaly, if you have been following this story, if you understand that we are witnessing something potentially historic, unfolding in real time, as December 19th approaches in just days, you need to subscribe to this channel immediately and turn on all notifications. New data is coming in constantly. Analyses are being published at an accelerating pace. The December 19th observation window will generate torrents of information that could finally provide definitive answers or could deepen the mystery beyond anything we have seen so far. You do not want to miss a single update. Hit subscribe, enable notifications, because what happens in the next few days might rewrite our understanding of what travels between the stars. Now let me walk you through Anomaly 16 and why it represents perhaps the most statistically troubling discovery yet. Something new just dropped about 3I Atlas. And I need you to understand that this is not a small technical detail, not an obscure measurement that only specialists care about, not a minor refinement of previous estimates. This is fundamental. This goes to the core of whether we can explain this object through natural processes, or whether we are confronting something that operates according to principles we have not previously encountered. It concerns the spin axis of the object, the invisible line around which this visitor from beyond rotates as it travels through space, the geometric pole that defines orientation and that determines which regions of the surface face the sun versus which remain in shadow. We have discussed spin axis before in previous coverage. We touched on rotation and orientation as part of understanding the anti-tail jet and the thermal environment on the nucleus, surface. But new analysis published just recently, detailed measurements that were not possible with earlier data, has revealed something about the spin axis configuration that is so geometrically specific, so statistically unlikely if occurring by random chance, that it forces us to add yet another entry to the growing catalogue of anomalies that this object exhibits. And when I explain what they found, when I walk you through the implications, you will understand why this discovery has generated intense discussion and why it pushes the boundaries of what coincidence can reasonably explain. The key concept here is spin axis alignment. That technical phrase describes how the rotation pole of an object, the axis around which it spins, is oriented relative to external reference directions like the direction to the sun or the direction of the object's motion through space. For most objects, for typical asteroids and comets, spin axis orientation is essentially random, or at least shows no special relationship to external directions, because there is no mechanism maintaining preferred orientation. Objects tumble, they precess, they undergo chaotic rotation changes driven by asymmetric forces from outgassing and impacts and tidal effects. Over long timescales, orientation randomizes unless something actively stabilizes it. But 3I Atlas, according to the new measurements, shows spin axis alignment that is not random, that exhibits geometric configuration far too specific to be easily dismissed as coincidence. The rotation axis points almost directly at the sun, maintains orientation where the spin pole aims sunward with precision, measured in single-digit degrees of deviation, creating configuration that has profound implications for thermal environment and for how we interpret the persistent anti-tail jet that has puzzled observers since early detection. And this alignment is not transient, not a momentary configuration that happened to be captured during brief observation window. It appears to have been maintained over extended periods, over millions of kilometers of orbital motion, suggesting stability that passive tumbling should not produce. Let me explain the technical basis for these conclusions, because understanding how researchers determined spin axis orientation from ground-based observations helps establish that this is robust finding, rather than speculation or artifact of analysis choices. You cannot directly see the rotation axis. It is not a physical feature that appears in images. It is geometric property inferred from observing how visible features change over time as the body rotates. The primary diagnostic here is the anti-tail jet, that mysterious sunward-pointing beam of material that we have discussed extensively in previous coverage as one of the most anomalous aspects of 3I Atlas. The anti-tail is not static. It is not a fixed structure frozen in space. Careful measurements of images taken at different times, precise determination of how the position angle of this feature changes across observation sequences, reveals that it wobbles. The jet direction, the line traced by the anti-tail in projected sky coordinates, shifts systematically following periodic pattern that repeats with specific measurable period. This wobble is small, confined to narrow angular range, but it is detectable with modern instruments and analysis techniques, and it carries enormous information about the source geometry. The research team measured position angle of the anti-tail at projected distance of 6,000 kilometers from the brightest peak of emission, from the central condensation that marks the nucleus location. 6,000 kilometers is about 3,700 miles, substantial distance that samples the jet structure well away from the immediate vicinity of the source, where measurements might be confused by complex near-nucleus features. At this distance, they are observing the collimated beam in a region where its trajectory has been established, where the direction accurately reflects source pointing rather than being affected by local perturbations. They then performed what is called phase folding, a mathematical technique where observations taken at many different times are mapped onto a single repeating cycle by using the measured period to determine where each observation falls within the rotation sequence. Imagine taking a long recording of something that repeats every hour and folding it so that all the first minutes line up, all the second minutes line up, and so on, creating averaged composite that shows the repeating pattern more clearly than any single observation. Phase folding suppresses noise and random variations while enhancing the periodic signal that actually repeats cycle after cycle. The result reveals wobble with period of 7.74 hours. That number is critically important and we will examine it more carefully shortly, but first understand what it means physically. 7.74 hours is the time required for one complete wobble cycle, for the jet direction to trace out whatever pattern it follows and return to starting configuration. And the most natural interpretation of this periodicity, the explanation that fits cleanly with all observations, is that this represents the rotation period of the nucleus, the time required for the solid body to complete one full spin around its axis. As the nucleus rotates, if the jet source is offset from the rotation pole, if it sits at some latitude away from the exact axis, then the jet direction will precess, will trace out a cone in space as rotation carries the source around the pole. The amplitude of this precession wobble, how wide the cone is, depends on how far offset the source is from the pole. Source exactly at the pole produces no wobble because it is on the axis and does not move as the body rotates around that axis. Source at the equator, 90 degrees from the pole, produces maximum wobble as it sweeps through large, circle during rotation. Intermediate offsets produce intermediate wobble amplitudes. The measurements reveal something remarkable. The wobble amplitude is small. The periodic variation in jet direction spans narrow angular range, indicating that the source is positioned very close to the rotation pole rather than at equatorial or intermediate latitudes. Detailed analysis of the wobble pattern, comparison with models that calculate expected precession for different source geometries, allows researchers to constrain the offset angle to determine how far from the pole the jet source must be to produce observed wobble characteristics. The result, less than 8 degrees. The base of the jet, the region on the nuclear surface where material is being ejected to form the anti-tail structure, lies within 8 degrees of the rotation pole. That is extraordinarily close in angular terms. To put it in perspective, 8 degrees is about 16 times the angular size of the full moon as seen from Earth. Not tiny, but certainly a narrow region on a spherical body. For the jet to originate from this near-polar position, rather than from random location anywhere on the surface, represents significant geometric constraint. Now here is why this matters profoundly. If the jet is coming from near the pole, And if simultaneously the jet points toward the Sun, which we know with absolute certainty because it forms an anti-tail structure extending sunward rather than being blown back by radiation pressure like normal cometary tails, then through basic geometry, we can deduce critical information about the orientation of the entire object. The rotation axis itself must be pointing approximately toward the Sun. The spin pole is aligned with the solar direction. Let me make this concrete with visualization. Imagine Earth, which rotates around an axis passing through geographic north and south poles. Now imagine we could tilt Earth's axis so that the North Pole pointed directly at the Sun, rather than being tilted 23.5 degrees, relative to the orbital plane as it actually is. In that configuration, if you were standing at the North Pole, the Sun would hang permanently in the sky at constant elevation, never rising or setting, providing continuous illumination. The South Pole would be in permanent darkness, never seeing the Sun, frozen in eternal night. This is essentially the configuration that 3i Atlas appears to be maintaining. One rotational pole points nearly directly at the Sun, staying in perpetual sunlight, continuously heated by solar radiation. The opposite pole points away from the Sun, remaining in permanent shadow, shielded from direct heating by the bulk of the object. And the jet, the mysterious anti-tail emission that has been visible for months, originates from near the sunward-facing pole, from the region receiving maximum and continuous solar input. Now, you might reasonably ask why this is problematic, why this specific geometric configuration represents an anomaly rather than just one of many possible orientations that the object might happen to have. The answer is statistical. If orientation were random, if spin axes of interstellar visitors point in arbitrary directions with no preference for alignment with external references, then the probability of finding an object with spin axis closely aligned with the Sun direction is very small, determined simply by solid angle geometry. Imagine all possible directions in three-dimensional space. The Sun occupies one specific direction from the comet's perspective. The fraction of all possible spin axis orientations that point within 8 degrees of that one specific direction can be calculated using basic spherical geometry. It turns out to be about 0.5%, 1 in 200. Those are not impossible odds. Rare events at 0.5% probability happen occasionally if you sample enough cases. But here is the critical context. We have only confirmed 3 interstellar visitors ever: Oumuamua, 2i Borisov, and now 3i Atlas. 3 objects, and one of them shows this rare alignment. That alone might be dismissible as luck if this were the only unusual feature, but it is anomaly number 16. It joins 15 other independently confirmed oddities spanning chemical composition, trajectory precision, jet collimation, thermal behavior, and structural properties. When coincidences stack, when multiple low-probability features all manifest simultaneously in the same object, statistical reasoning demands that we question whether pure chance remains adequate explanation, or whether some organizing principle, some physical mechanism, or perhaps something more intentional, might better account for the pattern we observe. And there is an additional crucial detail that makes the alignment even more striking. This is not a transient configuration. This is not a geometric relationship that just happens to be true at one instant during observations. The analysis indicates that the spin axis was already aligned with the Sun direction when 3i Atlas was still very far out, when it was beyond 5 astronomical units from the Sun approaching on its inbound trajectory before perihelion. 5 AU is 5 times the Earth-Sun distance, about 465 million miles, well outside the orbit of Mars, in the outer regions of the asteroid belt approaching Jupiter's domain. At those enormous distances, when the object was just barely warm enough for any activity, when solar heating was only 4% of what it would be at 1 AU perihelion, the alignment was already established. The pole was already pointing sunward. This tells us that the configuration is stable, that it persists as the object moves along its trajectory, covering tens of millions of kilometers. That orientation is not randomly tumbling on short timescales, but maintains this special relationship with the Sun direction, despite the enormous distance and despite forces that should perturb orientation. What physical mechanism could produce and maintain such alignment naturally? This is where explanations become strained. Normal comets tumble. Their rotation states are chaotic, driven by random perturbations from asymmetric outgassing that creates torques, from tidal effects during close approaches to planets or the Sun, from impacts with debris, from structural changes as volatiles sublimate and mass distribution shifts. Maintaining stable orientation, especially a specific alignment with external direction, rather than just maintaining arbitrary but fixed pointing, requires either extraordinary luck in initial conditions or some stabilizing mechanism that resists perturbation. One possibility is that the object has very particular shape and mass distribution that makes certain rotation states stable while others are unstable, similar to how elongated bodies preferentially rotate around their long axis, because that minimizes rotational energy for given angular momentum. But achieving stable sun pointing requires more than just shape effects. It requires that the preferred axis happens to be aligned with the sun, which brings us back to geometric coincidence requiring explanation. Another possibility is gyroscopic stability from rapid rotation. Objects spinning very fast have large angular momentum that resists changes in axis orientation, similar to how spinning gyroscope maintains its axis direction despite attempts to tilt it. But as we will discuss in detail later, 3i Atlas is not rotating particularly fast. The 7.74-hour period is leisurely by cometry standards, far too slow to provide strong gyroscopic resistance to perturbations. Slow rotation should make the object more susceptible to tumbling, not less, making the observed stability even more puzzling. A third mechanism that has been mentioned in discussions is that the anti-tail jet itself, the emission that we are using to infer orientation, might stabilize orientation through its reaction force and through interaction with solar wind. If the jet produces thrust that tends to maintain alignment, if the configuration is somehow self-stabilizing where deviations from sun pointing automatically generate torques that restore alignment, then perhaps the geometry can be stable even starting from random initial conditions. But this requires very specific properties, very particular relationships between jet thrust direction and center of mass and moment of inertia, stacking up more special requirements that must all be satisfied simultaneously. Each of these natural stabilization mechanisms is plausible in isolation. Each could in principle explain stable sun-pointing orientation, but each also requires specific conditions or specific properties that are not necessarily expected, and when you need multiple special circumstances all working together to explain one feature of one object out of only 3 interstellar visitors we have studied, skepticism about whether natural explanation is sufficient becomes reasonable rather than paranoid. Now let me show you the data directly. Let me walk through the observations that establish these conclusions so you can evaluate the evidence yourself, rather than just taking assertions on faith. The analysis is based on multi-epoch imaging, observations taken at many different times as the object moved along its trajectory and as rotation carried the jet source through its periodic wobble pattern. Each image captures the anti-tail at one instant, one specific phase in the rotation cycle, showing how the position angle varies. The images show 3i Atlas as a bright central condensation, the unresolved nucleus surrounded by diffuse coma, with the remarkable anti-tail extending as narrow linear feature toward the northwest in the typical image orientation, pointing in the direction of the sun rather than away from it as normal tails do. Superimposed on these images are various indicators. Purple lines mark the measured anti-tail position angle at the standard 6,000 kilometer distance, showing exactly which direction the feature points in sky coordinates for each observation. Red arrows indicate the projected velocity direction, showing which way the object is moving across the sky. Yellow arrows point toward the antisolar direction, directly away from the sun, which is where normal radiation pressure-driven tails should point. Orange lines show the derived projected rotation axis direction, the inferred orientation of the spin pole based on analyzing the wobble pattern across all observations. And critically, yellow lines trace the regular dust tail, the normal fan-shaped emission extending in the antisolar direction, where radiation pressure pushes dust particles away from the nucleus. The contrast between the narrow sunward anti-tail and the broad antisolar regular tail is stark in these images, emphasizing how anomalous the anti-tail structure is and how different its behavior is from standard cometry material. Multiple images spanning weeks of observations show consistent pattern. The anti-tail maintains its general sunward pointing. The position angle wobbles within narrow range following the measured 7.74-hour period. The regular tail behaves normally, pointing away from the sun as expected. Everything confirms that we are not seeing instrumental artifacts or analysis errors, not misinterpreting what is actually simpler geometry viewed from unfortunate angle. We are genuinely observing emission from near the rotation pole of an object whose spin axis points nearly at the Sun. Date stamps on images span from mid-November through mid-December, covering the period after perihelion as the object recedes from the Sun on its outbound trajectory. This temporal coverage is important because it demonstrates persistence of the configuration. This is not fleeting coincidence captured in brief observation window. This is sustained geometric relationship maintained as the object covers millions of kilometers, as viewing geometry changes substantially, as distance from Sun and from Earth evolves. The stability is real. Brightness contours overlaid on images show the intensity distribution of emitted light, revealing that the anti-tail is genuinely narrow, genuinely collimated, maintaining tight beam structure even at the 6,000 kilometer distance where position angle is measured. If this were diffuse emission or perspective effect, the contours would show broad distribution. Instead, they trace narrow ridge, dark linear feature extending from the bright nucleus toward the Sun, exactly what you would expect from directed emission, originating at localized source rather than from distributed outgassing across the entire nucleus surface. Let me now address a critical question that might have occurred to you as we discussed this geometric analysis. The measurements reveal properties of the projected spin axis, the axis direction as it appears in the two-dimensional images captured by telescopes. But three-dimensional orientation requires additional information beyond what single line of sight provides. How do we know the actual three-dimensional direction of the pole rather than just its projection onto the plane of the sky? The answer involves modelling the wobble pattern across multiple observations from different viewing geometries. As 3i Atlas moves along its orbit, as Earth moves in its own orbit, the relative viewing angle changes over time. This means we're observing the wobble from slightly different perspectives at different times. By fitting models that account for these changing geometries, by ensuring that the inferred spin axis orientation produces wobble patterns that match observations at all epochs, researchers can constrain the three-dimensional direction uniquely. The result places the spin axis within about 8 degrees of the Sun direction in three-dimensional space, not just in projection. This is robust finding, checked through multiple analysis approaches, verified by independent researchers examining the same data and reaching consistent conclusions. When I cite 0.5% probability for this alignment, that refers to the actual three-dimensional configuration, not to ambiguous projection that might result from variety of actual orientations. Now we must confront the immediate implication of this configuration, the physical consequence that flows directly from having spin axis, pointed nearly at the Sun with jet originating from near the pole. This geometry creates what is technically called obliquity, near 90 degrees, meaning the rotation axis is nearly perpendicular to the orbital plane, rather than being tilted at moderate angle like Earth's 23.5 degree obliquity, or lying nearly in the orbital plane like Uranus's extreme 98 degree obliquity. For 3i Atlas, perpendicular orientation means one pole continuously faces the Sun, while the other continuously faces away. The consequence is establishment of stable day side and stable night side, hemispheres that maintain roughly constant illumination rather than cycling between day and night as the body rotates. The sunward pole and its surrounding region bake in continuous solar heating, receiving photon flux that never switches off, driving volatile sublimation continuously rather than intermittently. Surface temperatures in this permanently illuminated region can reach equilibrium where incoming solar energy balances outgoing thermal radiation plus energy consumed by sublimation, creating stable thermal environment optimal for sustained gas production. The opposite hemisphere, shielded from direct sunlight by the bulk of the nucleus, remains cold, potentially at temperatures barely above those experienced during millions of years in interstellar space if thermal conduction through the nucleus is slow. Volatiles in the night-side region stay frozen, unable to contribute to gas production, essentially dormant until some change in orientation or in orbital geometry exposes them to solar heating. The asymmetry is profound, dividing the object into active and inactive hemispheres, rather than distributing activity more uniformly, as rotation exposes all regions to sunlight in normal configurations. This stable day-night division has enormous implications for understanding the persistent anti-tail jet. If the jet originates from the permanently heated pole, if it is driven by continuous sublimation from always illuminated surface, then its stability makes sense. It does not turn on and off with rotation cycle because the source never rotates into shadow. It does not show large variation in intensity because heating remains constant rather than cycling. It maintains steady emission that would be difficult to achieve if the source were located at equatorial or mid-latitude region that rotates through day-night cycle every rotation period. But this raises an uncomfortable question that we must face directly, a question that transforms curious geometric detail into profound anomaly. If stable day-night configuration is so advantageous for maintaining continuous jet emission, why would a natural comet happen to have this orientation? What evolutionary pathway or formational process would create it? And why would alignment persist over the enormous distances and timescales relevant to interstellar journey, followed by passage through stellar system? These questions don't have easy answers within standard framework of cometary origin and evolution. Natural processes produce chaotic outcomes, random orientation, random volatile distribution, random structural properties. Special configurations require special explanations, and when special configurations stack up, when we need multiple special explanations for multiple special features of the same object, parsimony begins to favor hypotheses that might initially seem exotic, but that explain many observations through single unified framework. We have established that 3I Atlas exhibits spin-axis alignment with the sun direction, maintained from at least 5 AU inward, creating stable dayside and nightside hemispheres, with jet originating from near the continuously illuminated pole. Now we must examine in forensic detail what this alignment means statistically, why the 0.5% probability matters so profoundly, and what observations would have looked like if the alignment were absent or weaker. Because understanding what we are not seeing, understanding what normal cometary behavior would have produced, is essential for grasping why this configuration represents genuine anomaly, rather than just interesting geometric detail. Let me start by establishing what 0.5% probability actually means in concrete terms, stripping away the abstraction of percentages and framing it in ways that connect to intuition about likelihood and coincidence. 0.5% is 1 in 200. If you had 200 interstellar comets arriving at random orientations, basic geometric statistics predict that only one of them would show spin axis aligned within 8 degrees of the sun direction. The other 199 would have axes pointing in different directions, distributed more or less uniformly across all possible orientations in 3-dimensional space, because there is no preferred direction that natural rotational dynamics favors. To visualize this geometrically, imagine the sphere of all possible directions. The sun occupies one specific point on this sphere from the comet's perspective. The region within 8 degrees of that point is a small cap, a circular patch that covers only a tiny fraction of the total spherical surface area. That fraction, calculated using standard solid angle formulas from spherical geometry, equals approximately 0.05, which is 0.5% when expressed as percentage. Any axis pointing within this small cap qualifies as sun-aligned. Any axis pointing outside this cap, which is 99.5% of the sphere, does not. Now, you might reasonably argue that 0.5%, while small, is not absurdly improbable. It is not like winning lottery with 1 in millions odds. It is more like rolling a specific number on 200-sided die, unusual but not impossible. And you would be correct that this single probability in isolation, taken as the only unusual feature of 3I Atlas, would not necessarily demand exotic explanations. Rare events happen. Low probability outcomes occur when you sample enough cases. The question is not whether 0.5% probability makes something impossible, but whether it makes it unlikely enough that we should pay attention when it occurs. But here is the critical context that transforms this from merely interesting to genuinely troubling. This is not occurring in isolation. This is anomaly number 16. It joins chemical composition anomalies showing elevated nickel ratios and organic abundances inconsistent with standard cometry, chemistry. It joins trajectory precision anomalies, where the path through our solar system appears targeted at dynamically significant locations, with accuracy that gravitational perturbation models struggle to explain naturally. It joins jet collimation anomalies where the antitail maintains coherence over 500,000 kilometers, despite forces that should disperse it. It joins thermal anomalies and structural anomalies and timing anomalies that we have catalogued in detail through previous coverage. When you stack multiple independent low-probability features, when you require numerous rare events to all manifest simultaneously, The joint probability collapses much faster than linear multiplication might suggest because you are sampling an increasingly small region of the total parameter space of possible object configurations. Each additional constraint eliminates most of the remaining possibilities, narrowing the allowable states to a tiny fraction of what random chance explores. This is why 16 anomalies is qualitatively different from 1 or 2 unusual properties. It is why careful statistical reasoning increasingly favours hypotheses that explain multiple observations through unified framework rather than invoking independent coincidences for each feature. But let us set aside for the moment the broader pattern of anomalies and focus specifically on the spin axis alignment itself, examining in detail what the alternative scenarios would have looked like and why the observations rule them out. This analytical approach, comparing what we actually observe against what competing hypotheses predict, is fundamental to scientific reasoning. It is how we distinguish between models, how we assess which explanations are consistent with data and which are contradicted by evidence. If the spin axis were not aligned with the sun direction, if orientation were instead typical for randomly tumbling cometary nuclei, several observable consequences would follow that we can enumerate and check against actual observations. First and most obvious, the anti-tail jet would not maintain nearly constant direction toward the sun as the body rotates. Instead, the jet would sweep across the sky following the rotation of its source region, creating either a fan-shaped or spiral structure rather than a narrow linear feature, or it would show strong periodic variations in brightness and position as the source rotates into and out of favourable orientations. Let me be more specific about what this looks like. Imagine a jet emanating from a surface patch at 45-degree latitude, halfway between equator and pole. As the nucleus rotates, this patch traces a circle around the rotation axis, sometimes pointing toward the sun, sometimes pointing sideways, sometimes pointing away from the sun. When it points directly sunward, we would see maximum jet intensity, because the geometry aligns for strong solar heating, and because the jet aims toward us providing optimal visibility. When it rotates to point perpendicular to the sun direction, heating would be reduced because solar flux strikes the surface at grazing angle rather than head-on, and our view of the jet would be edge-on, showing only narrow cross-section. When the source rotates to point away from the sun, it would be in shadow, receiving no direct solar heating, causing sublimation to cease or dramatically slow until the region rotates back into sunlight. The resulting light curve, the plot of brightness versus time, would show dramatic periodic variation with period equal to the rotation period, with brightness peaks when the jet points favourably and brightness minima during the shadowed or poorly oriented phases. The position angle of any resolved jet structure would swing through large range, tens of degrees or more, as the source sweeps around its circular path. We do not observe this behaviour. The anti-tail maintains relatively stable pointing toward the sun, showing only the small wobble consistent with source positioned within 8 degrees of the pole rather than at mid-latitudes. The brightness variations, while present and measurable for determining rotation period, are modest rather than dramatic, indicating that viewing geometry does not change drastically as rotation proceeds. This is exactly what near-polar source orientation predicts, and what equatorial or mid-latitude source would not produce. Second consequence of misalignment would be intermittent jet emission, turning on and off as the source region rotates through day-night cycle. Unless spin axis happens to point directly at the sun, which brings us back to the special alignment we are discussing, any given surface location will rotate into and out of sunlight with each rotation period. For an object with rotation period of 7.74 hours, each surface element would be illuminated for roughly half that time, about 4 hours, followed by 4 hours in shadow. Sublimation-driven jet emission depends strongly on surface temperature, which in turn depends on solar heating. When heating switches off, temperature drops and sublimation slows or stops, entirely depending on thermal inertia and volatile properties. The result should be jets that pulse, that show distinct on phases when the source is illuminated and off phases when it is in shadow. For very volatile species like carbon monoxide or nitrogen that sublimate at very low temperatures, the effect might be subtle, with emission continuing during shadowed phase, driven by thermal energy stored in near-surface layers. But for less volatile species like water or carbon dioxide that dominate most cometary outgassing, the on-off cycling would be pronounced. creating flickering jets that strengthen and fade with rotation period. We do not observe flickering. The antitail appears continuously in all images spanning months of observations. There is no evidence for intermittent emission, no periodic gaps or fading that would indicate the source, rotating into shadow. This continuous visibility is naturally explained if the source never rotates into shadow, if it remains continuously illuminated due to spin-axis alignment, but it contradicts expectations for misaligned tumbling body, where day-night cycling should modulate emission. Third, and more subtly, misalignment would affect the collimation of the jet in ways that should be detectable. If the source were at mid-latitude rather than near the pole, if it were rotating through varying orientations relative to the sun direction, then the direction of peak solar heating would change during the rotation cycle. This varying heating geometry would produce jets with varying ejection directions, not a single stable beam but a more complex pattern, where material leaves the nucleus at different angles at different rotation phases. The integrated effect over multiple rotation periods would be to create broader, more dispersed structure rather than the tightly collimated beam we observe extending 500,000 kilometers sunward. Think of it like a garden sprinkler with a single nozzle mounted off-center on a rotating platform. As the platform spins, the water jet sweeps out a cone, with water droplets ejected in all directions over the full rotation cycle. The result is circular spray pattern, not a narrow beam. For 3i Atlas to maintain narrow beam despite rotation requires that the jet source either does not sweep significantly as the body rotates, which means it must be near the rotation axis, or that emission is somehow timed to occur only when orientation is favourable, which requires explaining the timing mechanism. Observationally, the antitail shows remarkable collimation, narrow linear structure maintained over enormous distances. Spectroscopic observations that could measure velocity dispersion and angular spreading have not yet been conducted with sufficient resolution to definitively characterize these properties. But the morphological evidence from images is clear. We see narrow beam, not broad cone or fan. This is consistent with near-polar source that remains pointed sunward as the body rotates around that direction, but inconsistent with randomly oriented source sweeping through various directions. Fourth consequence involves geometric foreshortening and projection effects. When viewing an object whose spin axis is significantly tilted relative to our line of sight, we see rotating features trace ellipses or complex curves in the image plane rather than simple circles. The projection geometry creates distortions that should be detectable in careful analysis of how features move as rotation proceeds. Conversely, when spin axis points nearly toward or away from observer, rotation appears as simple circular motion without strong foreshortening. For 3i Atlas, the spin axis points nearly toward the Sun, and from Earth's perspective during most observations, we are viewing the system from angles that provide good view of the jet axis geometry. The wobble pattern observed in position angle measurements follows the relatively simple sinusoidal variation expected for precessing polar jet, without complex multi-component variations that would indicate significant projection effects from tilted axis. This geometric consistency provides additional constraint confirming that the inferred orientation is physically accurate rather than artifact of assuming simplified geometry. Now let's examine what the observations actually show in detail, walking through the multi-panel imaging data that documents the jet behavior and confirms these conclusions. The images I referenced earlier, the sequence of observations spanning weeks of coverage, reveal consistent pattern that eliminates alternative explanations and establishes that we are genuinely observing the special geometric configuration rather than misinterpreting more conventional behavior. Each panel in the sequence shows 3i Atlas at a different date and time, with specific UTC start and end times noted along with the number of exposures that were combined to create each image. Multiple exposures are stacked to increase signal-to-noise ratio, allowing detection of faint features that would be lost in noise of individual short exposures. The image quality is variable, reflecting different atmospheric conditions and different telescope capabilities used for various observations, but the key features are consistently visible across the entire sequence. The purple lines marked on each image trace the measured anti-tail position angle at the standard 6,000 km distance, showing where the analysis measured the jet direction for that particular observation. These lines do not all point in exactly the same direction. They show systematic variation, the wobble we have been discussing, as the position angle shifts following the 7.74-hour periodic pattern. But crucially, the variation is small, confined to narrow angular range rather than swinging wildly across large angles, as would occur if the source were at mid-latitude or if the axis were significantly misaligned. The red arrows indicating projected velocity direction show which way the comet is moving across the sky in each image. This velocity vector changes slowly as the orbital motion carries the object along its path and as Earth's own motion alters viewing geometry. The antisolar direction, marked with yellow arrows, similarly varies as the relative positions of the comet and Sun change over time. Despite these changing external reference directions, the anti-tail consistently maintains its characteristic sunward pointing, tracking the sun direction as both the comet and viewing geometry evolve. Most tellingly, the derived rotation axis direction, shown as orange lines, maintains remarkably stable orientation across the observation sequence. This is the critical finding, despite covering weeks of time, despite spanning millions of kilometers of orbital motion, despite viewing geometry changes and rotation carrying the object through thousands of complete spins. The inferred axis direction does not wander randomly or precess significantly. It stays locked, pointing approximately toward the Sun within the narrow tolerances that the 8-degree offset allows. This stability is not what we expect from passive tumbling body, experiencing random perturbations from outgassing forces and gravitational torques and impacts with interplanetary dust. Passive bodies should show axis precession, slow drift in orientation as perturbations accumulate over time. The fact that we do not observe significant precession, that the orientation remains stable, indicates either that perturbations are remarkably weak, which seems unlikely given the strong jet emission that must be creating substantial thrust and torque, or that some stabilization mechanism is operating, maintaining the alignment against disturbances that would otherwise randomize orientation. The brightness contours overlaid on images reveal intensity distribution in the coma, showing how light is distributed around the central condensation and how it extends along the anti-tail. The contours are drawn at multiple levels, from 20th percentile, faint extended emission, through 95th percentile, bright concentrated regions, allowing visualization of both the diffuse coma and the sharply peaked nucleus plus anti-tail structure. The anti-tail appears as elongated feature in the contours, maintaining tighter columnation than the surrounding diffuse emission, confirming that this is genuinely focused jet rather than just preferential viewing geometry, making normal diffuse emission appear linear through projection effects. Now, I want to address a specific technical question that careful observers might raise when examining these images. The brightness of the anti-tail appears to vary somewhat between different observations, with some images showing more prominent structure than others, even after accounting for differences in exposure time and image processing. Does this variability indicate intermittent emission, contradicting my earlier claim that the jet is continuous rather than pulsing with rotation period? The answer is that apparent brightness variations are expected even for continuous jet due to several factors unrelated to intrinsic emission changes. First, viewing geometry affects how much of the jet length projects into our line of sight versus extends perpendicular to it. When the jet axis aligns more closely with our viewing direction, we see down the length of the beam through more material, increasing integrated brightness. When the axis is more perpendicular to our line of sight, we see the beam in profile through less material, reducing apparent brightness even if the intrinsic emission rate is unchanged. Second, sky background conditions affect contrast between jet and surrounding sky. Observations made during bright twilight or with moon present in the sky show higher background levels that reduce effective signal-to-noise ratio even if the comet itself is equally bright. Comparing images taken under different background conditions requires careful, photometric calibration to account for these variations. Third, atmospheric seeing conditions and telescope tracking accuracy affect how well the faint extended features like the anti-tail are captured versus being blurred by motion or turbulence. When these factors are properly accounted for, when photometric measurements are normalized to common standards, and when only high-quality data are compared, the anti-tail brightness shows much less variation than raw images suggest. The structure is persistently present across all good observations, without evidence for the complete disappearance or dramatic fading that intermittent emission driven by rotation into shadow would produce. This consistency supports the continuous emission model that near-polar source naturally explains. Let me now quantify more carefully the implications of the 0.5% probability in the specific context of interstellar objects and our limited sample size. We have confirmed 3 interstellar visitors: Oumuamua, with its own profound anomalies including unexplained non-gravitational acceleration and highly elongated shape; 2II Borisov, which appeared much more conventionally comet-like despite its interstellar origin; and now 3I Atlas with its catalogue of unusual features. 3 objects constitute extraordinarily small sample from which to draw statistical conclusions about what is typical versus rare for interstellar visitors. If we assume that these 3 are representative sample, drawn from much larger population of interstellar objects passing through the solar system, and if we treat spin axis orientation as independent random variable uncorrelated with other properties, then observing one object with sun-aligned axis out of 3 is somewhat more than the 0.5% baseline probability would predict. We might have expected to need to observe 200 objects before seeing this rare configuration once. Seeing it in just 3 suggests either that we got very lucky, drawing a rare case from small sample, or that the baseline probability is actually higher than geometric calculation predicts, meaning alignment is not truly random. Why might alignment be non-random? Several speculative mechanisms could in principle create bias towards sun alignment. If objects became active only when spin axis happens to be favourably aligned, with dormant objects remaining undetected, then observed sample would be biased toward aligned cases even if underlying population has random orientations. But this selection effect seems contrived, requiring explaining why activation would depend on axis orientation in the first place. Alternatively, if there were physical process during approach to stars that tends to align spin axes with stellar direction, perhaps through gravitational torques or through radiation pressure torques acting on asymmetric shapes, or through outgassing feedback that reorients objects towards stable configurations, then sun-aligned axes might be more common in observed population than geometric probability suggests. Such mechanisms have been proposed in theoretical studies, but they generally require rather specific conditions to work effectively, and they do not obviously apply to objects like 3I Atlas that were already aligned at large distances before strong alignment forces would be expected to operate. The alternative interpretation, the one that does not require invoking new physics or complex selection effects, is that 3I Atlas is not randomly oriented natural object, but is instead something that maintains specific orientation intentionally for functional reasons. If it is artificial probe rather than natural comet, if it has active attitude control systems or passive stabilization mechanisms designed to maintain sun pointing for thermal management or power generation or communication purposes, then the alignment is not coincidence but design feature. The 0.5% probability evaporates because we are not sampling random distribution but observing engineered configuration. This brings us to the central tension in interpreting all the accumulated anomalies. Each individual feature can be explained naturally if we accept low enough probability and invoke sufficiently specific special circumstances. The spin axis alignment is rare but possible. The chemical composition is unusual but not impossible. The trajectory precision is improbable but not ruled out. The jet collimation is puzzling but might have exotic natural explanation we have not yet identified. Taken individually, none of these anomalies definitively proves artificial origin, but when we combine them, when we ask what is the joint probability that all 16 anomalies occur together in the same object by chance alone, the numbers become vanishingly small. Multiply 0.5% by the probabilities for all the other unusual features, accounting for the fact that some may be correlated rather than independent, and you get joint probability far below the threshold where unlikely but possible remains credible explanation. At some point, which reasonable people can debate about where exactly the threshold lies, stacked improbabilities become sufficient evidence to seriously consider alternative hypotheses that initially seemed more exotic, but that explain observations more parsimoniously. I want to emphasize that I am not claiming to have definitive proof of artificial origin. The evidence remains circumstantial rather than conclusive. But I am arguing that the artificial hypothesis deserves serious investigation rather than reflexive dismissal, that the accumulating weight of anomalies has shifted it from wild speculation to viable working hypothesis that explains data better than increasingly strained, natural explanations requiring ever longer chains of coincidence and special circumstance. Science advances by following evidence honestly wherever it leads, and the evidence concerning 3I Atlas is leading toward territory that makes many researchers uncomfortable, but that cannot be ignored if we are serious about understanding what we're observing. As we prepare to move to the next section of our analysis, as we shift from discussing the pre-perihelion alignment to examining what happened after the object swung around the Sun and began its outbound journey, I want to leave you with a clear sense of where we stand. The spin-axis alignment during inbound approach, maintained from at least 5 AU inward, creating stable dayside and nightside, enabling continuous jet emission from near-polar source, represents significant anomaly, with probability around 0.5% if orientation is random. Alternative explanations requiring either selection effects or novel alignment mechanisms face challenges in explaining observations without introducing additional assumptions that themselves require justification. And this is just the inbound geometry. What happened after perihelion, when the object's position relative to the Sun changed by 180 degrees as it swung around and began receding, compounds the mystery further and pushes the probabilities to even more extreme levels, as we'll see in the next chapter, when we examine the post-perihelion behavior and what it implies about either extraordinary natural coincidence or about properties inconsistent with standard cometary physics. We have established that the pre-perihelion spin-axis alignment represents a 1 in 200 coincidence, if orientation is random, a configuration that enabled continuous jet emission from permanently illuminated polar region as 3I Atlas approached the Sun from interstellar space. But orbital mechanics creates an unavoidable geometric transformation as objects swing around the Sun at perihelion. The trajectory curves. The object's position relative to the Sun changes by approximately 180 degrees, and if the spin axis maintains fixed orientation in space, as gyroscopic stability or as passive tumbling would naturally produce, then the geometric relationship between axis and Sun must change correspondingly. The pole that pointed sunward during approach should point away during recession. The stable day side should become the night side, and vice versa. This is not speculation or theoretical possibility. This is mathematical certainty dictated by how angles work in three-dimensional space when you move along curved trajectory around a central body. Imagine walking in a circle around a lamppost while holding your arm extended, pointing in a fixed direction relative to the stars. When you start your circle with arm pointing toward the lamp, by the time you've walked halfway around the circle to the opposite side, your arm now points away from the lamp even, though its direction relative to the stars has not changed. The lamp has moved from in front of you to behind you due to your motion around it. Your arm's fixed orientation means it cannot track both your original direction and the lamp simultaneously. For 3I Atlas, the same geometric logic applies. If the spin axis pointed toward the Sun during July and August, when the object was inbound at distances beyond 2 AU, approaching perihelion, and if that axis maintained fixed orientation in inertial space, as the object swung around the Sun and began receding on the outbound leg of its trajectory, then by November and December, when observations show the object at 1.5 to 2 AU outbound, the axis should now point away from the Sun rather than toward it. The geometric configuration should have flipped. The stable day side should have moved to the opposite hemisphere. And here is where the mystery deepens profoundly, where observations contradict what this simple geometric analysis predicts, where we are forced to either invoke a second extraordinary coincidence or to seriously consider that something about our understanding of this object is fundamentally incomplete. The anti-tail jet persists after perihelion. It does not disappear or weaken significantly. It continues pointing toward the Sun, maintaining its characteristic narrow collimation, visible in Hubble Space Telescope images from November and December, confirmed by ground-based observations from multiple independent facilities, documented in the December 15th and 16th data that shows the jet extending 500,000 kilometers sunward, with the same morphological properties it exhibited during inbound approach. Let me be absolutely clear about why this is problematic, why continuation of sunward jet activity after perihelion represents a profound challenge to natural explanations. If the jet originates from near the rotation pole, as the wobble analysis conclusively demonstrates, and if the same pole that was continuously illuminated during inbound approach is now on the night side after the 180-degree flip in orbital position, then that original active region should be inactive, cold, frozen, no longer receiving the solar heating that drove sublimation and jet formation during July through October. The jet we observe post-perihelion, if it is being produced by the same mechanism as the pre-perihelion jet, cannot be coming from the same pole. It must be coming from a different region on the nucleus, specifically from a region that is now facing the Sun in the new post-perihelion geometry. And given that the jet shows the same near-polar characteristics, the same tight collimation, the same stable pointing toward the Sun despite rotation, this new active region must also be located near a rotation pole, must also be positioned within about 8 degrees of the spin axis. The only way to maintain sunward jet from near polar source both before and after perihelion, given the 180-degree flip in geometric configuration, is if the object has 2 separate major volatile reservoirs, 2 distinct ice pockets or venting regions, one near each rotation pole, one at the North Pole, and one at the South Pole, and if these 2 regions activate sequentially, with the pre-perihelion pole driving activity during inbound approach, and then shutting down as it rotates into shadow, while simultaneously the post-perihelion pole activates as it rotates into sunlight, creating seamless handoff that maintains continuous sunward emission, despite complete reversal of geometric configuration. Now let us carefully examine the probability of this occurring naturally, of having not just one but 2 major volatile deposits positioned at opposite poles of a small nucleus, both located within the narrow angular zone required to maintain observed jet characteristics. The probability of the first pole having its ice pocket within 8 degrees of the rotation axis, as we discussed extensively in previous chapters, is approximately 0.5%. This is geometric probability based on solid angle, independent of any assumptions about how volatiles are distributed on cometary nuclei. For the second pole to also have major ice pocket within 8 degrees of its rotation axis, we face the same geometric constraint. The probability is again 0.5%, or 0.005 when expressed as decimal fraction. But these are not independent probabilities in the sense of separate unrelated events. We need both conditions to be satisfied simultaneously in the same object to explain the observations. We need the first pole and the second pole to both have appropriately positioned volatiles. When calculating joint probability of multiple independent conditions, when asking what is the likelihood that event A and event B both occur, standard probability theory tells us to multiply the individual probabilities. 0.05 times 0.05 equals 0.0025. Converting back to percentage, this is 0.02%. Expressing as odds, this is 1 chance in 40,000. Let me repeat that for emphasis. 1 in 40,000. The probability that a randomly configured cometary nucleus would have major ice pockets positioned within 8 degrees of both rotational poles purely by chance is 1 in 40,000. This is no longer in the realm of unlikely but possible coincidences that we might observe occasionally if we sample enough objects. This is entering territory of statistical absurdity, where invoking pure chance as explanation becomes almost unreasonable. To put this in context, consider that we have only observed 3 confirmed interstellar objects in all of human history. We would need to observe tens of thousands of interstellar visitors, documenting their properties with the level of detail we have achieved for 3i Atlas, before we should expect to see one that exhibits this particular combination of geometric configurations by random chance. Yet we are seeing it in object number 3. The third interstellar visitor we have, confirmed and studied, shows this extraordinarily improbable feature. Either we are witnessing a statistical miracle, drawing the rarest possible card from a deck we have barely begun to sample, or the underlying assumption that configuration is random is incorrect, meaning that some mechanism, either natural or artificial, creates or maintains these specific geometric properties in ways that make them far more probable than geometric calculation suggests. Let me make the argument even more stark by considering what additional conditions must be satisfied beyond just the geometric positioning of ice pockets near both poles. The timing must also be precise. The pre-perihelion polar region must remain active throughout the inbound approach, maintaining continuous emission from July through October as solar distance decreased from beyond 5 AU down to 1 AU at perihelion. Then, at perihelion or shortly thereafter, as geometric configuration flips, the first region must shut down or dramatically reduce its activity, while simultaneously the second region activates, beginning to produce sunward jet with comparable intensity and collimation. For natural comet driven purely by solar heating and thermal response of volatile ices, this timing sequence requires explaining why the second pole remained dormant, during inbound approach, despite receiving some level of solar illumination as the object rotated, why it did not become active earlier when heating would have been sufficient to mobilize volatiles, and why it activated precisely when geometric configuration changed in a way that made it necessary to maintain sunward jet visibility. The synchronization seems almost choreographed, as if the object knew when to switch active regions to preserve the anomalous behavior we are observing. One could propose that the second pole was covered by insulating dust mantle, or refractory crust that prevented volatiles from sublimating until perihelion heating became intense enough to breach or erode this protective layer, exposing fresh ice that could then outgas. But this explanation requires that the crust thickness and thermal properties were precisely tuned to fail at perihelion rather than earlier or later, and it requires that this fortuitously timed breakthrough occurred at the geometrically special location within 8 degrees of the pole, rather than at some other location on the hemisphere. Alternatively, one could propose that volatiles at the second pole are supervolatile species like carbon monoxide or nitrogen that were stable even under the heating experienced during inbound approach at the solar distances the object traversed, but that crossed their sublimation threshold only at the intense heating near perihelion, triggering sudden activation. But this requires explaining why these supervolatiles, which should have been lost during any prior close stellar approaches in the object's origin system, were preserved specifically at polar locations on both sides of the nucleus and nowhere else in significant quantities. Each proposed natural mechanism introduces its own stack of required special circumstances, its own set of low probability conditions that must be satisfied. We are not just multiplying the 0.5% probabilities for geometric positioning. We are multiplying those by additional factors for thermal properties, for volatile composition, for crust structure, for timing synchronization, for all the auxiliary conditions that must align to produce the observed behavior through purely passive response to solar heating. The joint probability for all these factors collapses to values far smaller than the already tiny 0.0025% we calculated from geometric considerations alone. Now let me show you what the post-perihelion observations actually reveal, examining the imaging data that confirms the jet persists and that its properties remain consistent with polar source, rather than showing the dramatic changes we would expect if activity had shifted to different regions. The Hubble Space Telescope images from mid-November, taken roughly 2 weeks after the October 29th perihelion, show the anti-tail prominently visible extending sunward with the characteristic narrow linear morphology we saw in pre-perihelion observations. Ground-based observations from major facilities, including Gemini Observatory and various professional and amateur telescopes coordinating through International Astronomical Union circulars, show consistent picture. The anti-tail is there. It points toward the sun. It maintains tight collimation. The structure that should have disappeared or dramatically transformed after the geometric flip has instead persisted essentially unchanged, exhibiting the same anomalous properties post-perihelion that made it noteworthy pre-perihelion. Most tellingly, the December 15th and 16th observations, the most recent data as of this recording, show the anti-tail extending to distances exceeding 500,000 kilometers, maintaining collimation that continues to defy explanation through standard gas dynamic and radiation pressure models. This is not fading remnant structure, not trailing materials slowly dissipating after active emission ended. This is continuous jet, actively maintained, requiring ongoing mass loss from the nucleus to replenish material that solar wind and radiation pressure would otherwise disperse on timescales of hours to days at these distances from the sun. The inference is inescapable. Something on the nucleus is actively outgassing now in mid-December, nearly 7 weeks after perihelion, maintaining the sunward jet despite the changed geometry that should have terminated emission from the originally active polar region. And given that the jet shows the same near-polar characteristics, the same tight collimation, the same wobble pattern indicating source within 8 degrees of rotation axis, this new active source must be geometrically similar to the original one, positioned at the opposite pole in the only configuration that allows sequential handoff while preserving observed jet properties. Let me address a potential counter-argument that skeptics might raise. Could the observed post-perihelion jet be residual material, dust and gas ejected during pre-perihelion activity that remains visible in images due to slow dispersion, even though active emission from the nucleus has ceased? Could we be seeing ghostly afterglow rather than continuing activity, mistaking trails for active jets? The answer is definitively no for several reasons. First, the high-resolution images show the jet extending continuously from the bright central condensation that marks the nucleus. There is no gap, no separation between the bright source and the jet structure. Residual material would create trails that start at the location where emission occurred, which was the nucleus position at time of emission, but would then drift away following ballistic trajectories or being pushed by radiation pressure. We should see offset between current nucleus position and where the trail begins if we're observing old material rather than active emission. Second, the longevity of the structure argues against residual interpretation. Solar wind and radiation pressure act continuously on ejected material, accelerating it and dispersing it. Faint dusty trails from comet outbursts are typically visible for days to weeks before dispersing below detection threshold. The 3i Atlas anti-tail has been continuously visible for months, from initial detection in July through mid-December, spanning roughly 150 days. This extended persistence requires continuous or near-continuous replenishment through active outgassing, not one-time ejection events leaving gradually fading trails. Third, spectroscopic observations when available show emission lines from gas molecules, indicating presence of volatiles being actively excited by solar UV radiation. Residual dust would not produce molecular emission lines. The detection of gas signatures confirms ongoing sublimation from the nucleus, rather than just inert dust trailing behind, supporting the active jet interpretation rather than residual material explanation. The post-perihelion activity is real. The jet is active, the nucleus is outgassing, and the implications for natural versus artificial origin are profound because the sequential activation of antipodal polar sources with precise timing and with preservation of anomalous jet properties through the transition represents yet another stacked coincidence added to the already lengthy list of improbabilities we must accept if maintaining that 3i Atlas is purely natural comet. Let me now introduce another dimension to this analysis, examining not just the static geometric configuration, but the dynamic behavior during the perihelion transition itself, because observations from late October and early November provide crucial constraints on how rapidly the switchover occurred and whether it shows characteristics of gradual thermal evolution or of more abrupt transition suggesting active control. If the switchover is purely thermal response to changing solar heating geometry, we expect a transition period where both poles show some activity. As the pre-perihelion pole rotates into shadow and begins cooling, thermal inertia means it remains warm for some time, continuing to outgaze at reduced rates even after direct solar illumination ceases. Meanwhile, as the post-perihelion pole rotates into sunlight, it takes time to warm up, time for heat to conduct into subsurface ice layers, time for sublimation to ramp up to the rates necessary to produce visible jet. The overlap period where both poles are partially active should produce observable signatures. We might see the jet bifurcate temporarily, showing two components pointing in slightly different directions corresponding to emission from both poles simultaneously. Or we might see brightness variations as the combined emission fluctuates during the handoff. Or we might observe period of reduced overall activity as the strong pre-perihelion source fades before the post-perihelion source reaches full strength. Observations from the perihelion window, while not as densely sampled as we would ideally like due to the object's proximity to the Sun, in the sky, making observations difficult, show remarkably smooth transition. The brightness curve does not show dramatic dips or gaps. The jet morphology does not show obvious bifurcation or complex multi-component structure. The handoff appears seamless within the time resolution and sensitivity limits of available data, suggesting either that thermal response times are much faster than standard models predict, or that some coordinating mechanism ensures smooth transition rather than chaotic overlap or gap. This temporal behavior compounds the improbability. Not only do we need two antipodal polar ice pockets with geometric positioning that already carry 0.025% probability, but we also need the thermal properties and volatile characteristics tuned such that the transition between them occurs smoothly and rapidly, producing continuous jet emission throughout perihelion passage, rather than showing the intermittent or complex behavior that uncoordinated thermal response would more naturally create. Every additional constraint, every additional requirement that observations impose on natural explanation multiplies into the joint probability calculation, driving it to levels where rational assessment must acknowledge that we're no longer dealing with unlikely but possible coincidence, but with something that demands explanation beyond invoking fortunate alignment of multiple independent rare events. Now I want to directly address the uncomfortable question that follows from this probability analysis. If natural explanation requires accepting 1 in 40,000 odds just for the geometric configuration, with additional factors for timing and thermal properties driving joint probability even lower, at what point do we acknowledge that the artificial hypothesis, despite initially seeming more exotic, actually becomes the more parsimonious explanation, because it explains all observations through single unified framework of intentional design, rather than through stacking coincidence upon coincidence? This is not argument from ignorance, not claiming that because we cannot easily explain something naturally it must therefore be artificial. This is argument from probability and parsimony, recognizing that when natural explanation requires numerous specific conditions that must all simultaneously be true, each adding its own low probability requirement, the joint likelihood becomes vanishingly small, potentially smaller than reasonable prior probability we might assign to artificial origin, even if we start with strong skepticism about encountering alien probes. Bayesian reasoning provides formal framework for this kind of analysis. Start with prior probabilities for natural versus artificial origin. Update these priors based on observations, asking how much more likely the observations are under one hypothesis versus the other. If observations are dramatically more probable under artificial hypothesis, if they require much less fine-tuning and fewer special assumptions, then posterior probability shifts toward artificial even if prior was heavily weighted toward natural. The key question is not whether artificial origin seems intuitively unlikely, based on our lack of prior experience with alien probes. The key question is whether it is more or less unlikely than the specific combination of circumstances that natural explanation requires to account for the observations. And when natural explanation demands 1 in 40,000 geometric coincidence plus additional timing and composition requirements, when it requires that we got extraordinarily lucky in the third interstellar object we ever observed, the artificial hypothesis, which explains observations straightforwardly through design features intended to maintain specific orientation, and behavior begins to look more rather than less probable, despite its exotic implications. I want to emphasize again that I am not claiming definitive proof. The evidence remains circumstantial. We have not detected unambiguous signatures like radio transmissions or resolved geometric structure that would remove all doubt. But the weight of accumulated probability arguments, the sheer number of coincidences required for natural explanation, creates compelling case for taking artificial hypothesis seriously as working model rather than dismissing it reflexively as too extraordinary to consider. As we move to the final chapter of this analysis, as we examine what the December 19th closest approach observations might reveal and what implications either natural or artificial origin carries for our understanding of galactic civilization and for humanity's cosmic context, I want you to carry forward clear awareness of where the probability analysis has led us. We started with 1 in 200 odds for spin-axis alignment during inbound approach. We then discovered that maintaining similar behavior post-perihelion requires second similar configuration, squaring the probability to 1 in 40,000. And this is just the geometric component. Add timing, add composition, add all the other anomalies in the catalogue, and we are dealing with joint probability so small that treating it as coincidence requires either accepting statistical miracle or questioning fundamental assumptions about what we are observing. We have traced the geometric improbability from 1 in 200 odds for the pre-perihelion alignment to 1 in 40,000 odds for the dual pole configuration required to explain post-perihelion behavior, compounding probabilities to levels where natural coincidence becomes increasingly difficult to defend as adequate explanation. Now we must confront what this means practically, what observations we should expect during the December 19th closest approach that could distinguish between competing hypotheses, and why the institutional silence from major space agencies about these profound anomalies represents failure of scientific communication that demands accountability. Let me start with the rotation period, reconciliation, because this technical detail has generated confusion, and because understanding it properly provides crucial context for everything else. The wobble analysis that revealed the near-polar jet source indicates a 7.74-hour periodicity in the position angle variations. This is half of the approximately 15.5-hour rotation period that was independently derived from brightness variations observed during July and August, when the object was inbound. Why the factor of 2 difference? What does it tell us about the nucleus structure and activity? The most straightforward explanation is that the nucleus has 2 active regions, not just one, positioned at opposite poles as we have been discussing. If both poles have volatile deposits, and if both become active under appropriate illumination conditions, then as the nucleus completes one full rotation, we observe 2 brightness peaks corresponding to when each pole rotates into favourable orientation for our viewing geometry. The 7.74-hour wobble period represents the time between successive pole presentations, while the true rotation period is double that, 1548 hours, representing the time for the nucleus to complete 360-degree rotation, returning the same pole to the same orientation. This interpretation reconciles the seemingly discrepant measurements, and it is entirely consistent with the dual-pole model we have been discussing. The pre-perihelion and post-perihelion jets originate from these 2 antipodal sources, activated sequentially as geometric configuration changes. The 15.5-hour rotation period that earlier photometrics analysis suggested is essentially identical to the doubled 7.74-hour wobble period, differing by less than 1%, well within measurement uncertainties. The consistency validates both measurements and confirms that we are correctly interpreting the geometric configuration. Now, what does this rotation rate tell us about mechanical forces on the nucleus? The rotation period of 15.5 hours combined with estimated nucleus radius of approximately 2 kilometers allows calculation of the surface velocity at the equator, the linear speed at which equatorial surface features are moving due to rotation. The result is roughly 0.22 meters per second, about half a mile per hour, slower than typical human walking pace. This is leisurely rotation by any standard, far slower than the rapid spin of many small asteroids that can have rotation periods measured in minutes or hours. From this rotation rate we can calculate centrifugal acceleration at the equator, the outward force per unit mass that rotation creates trying to fling material off the surface. The formula is straightforward. Acceleration equals velocity squared divided by radius. Plugging in the numbers gives centrifugal acceleration of approximately 0.0024 meters per second squared, which is 0.0004 centimeters per second squared in the units often used in planetary science. This is extraordinarily tiny, about 2.5 millionths of Earth's surface gravity. What this means practically is that rotation creates essentially negligible mechanical forces. The centrifugal effect is far too weak to assist in ejecting material from the surface or to contribute meaningfully to volatile mobilization. Jets and outgassing must be driven purely by sublimation pressure, by the expansion of gas as ices transition from solid to vapor phase, without any mechanical boost from rotation. This rules out explanations that might invoke rapid spin helping to launch material, and it means that the activity we observe requires sufficient volatile content and sufficient heating to drive sublimation forcefully enough to overcome the nucleus's weak gravity without assistance from rotation. The weak centrifugal force also has implications for artificial gravity if we entertain spacecraft hypothesis. Some concepts for long-duration space missions propose using rotation to create artificial gravity, spinning the vehicle to produce centrifugal acceleration that crew members experience as gravity-like force, pulling them toward the outer hull. For 3I Atlas, with its current rotation rate, the artificial gravity at the surface would be those 2.5 millionths of Earth gravity, completely imperceptible, orders of magnitude too weak to provide any physiological benefit for biological crew or even to affect how liquids behave. To generate Earth-like artificial gravity, to produce one standard g of acceleration at the surface of a 2-kilometer radius object, would require a rotation period of only about 90 seconds, nearly 600 times faster than the observed 15.5-hour period. The current rotation is far too slow to serve artificial gravity purpose, suggesting that if this is spacecraft rather than natural comet, it is not designed for biological crew requiring gravity simulation, but is more likely robotic probe or perhaps derelict artifact no longer maintaining its original functional configuration. Now let us turn to the critical questions about institutional response and scientific communication, because the silence from major space agencies, particularly NASA, which has traditionally led discussion of solar system exploration and planetary defense, is conspicuous and troubling, given the magnitude of the anomalies we have documented. NASA has issued brief press releases noting that 3I Atlas is being observed and that it represents the third confirmed interstellar visitor. But these statements provide minimal technical detail, and they do not address any of the 16 anomalies that have been independently verified by researchers analysing publicly available data. This lack of detailed public discussion is striking contrast to how NASA handled previous interstellar objects. Oumuamua generated extensive NASA commentary, including detailed technical presentations explaining the unusual acceleration and the various hypotheses proposed to account for it. Tuii Borisov received regular updates as observations accumulated, with NASA scientists prominently featured discussing what we were learning about comets from other stellar systems. But 3I Atlas, despite exhibiting far more numerous and more profound anomalies than either predecessor, has received comparatively minimal institutional attention. Why the silence? Several possibilities exist, and we cannot definitively determine which factors are most important without internal access to agency decision-making processes. One possibility is that the anomalies are so bizarre, so difficult to explain within conventional frameworks, that institutional caution prevents public discussion until consensus explanation emerges. Space agencies are risk-averse organizations that generally avoid making statements that might later prove embarrassing if observations are reinterpreted or if initial analyses contain errors. Facing data that seems to challenge basic assumptions, the safe institutional response is silence until the picture clarifies. Another possibility is that artificial hypothesis, despite its statistical support from probability analysis, remains too politically sensitive to discuss openly even as possibility worth investigating. The implications of confirming extraterrestrial technology would be profound, extending far beyond astronomy to touch every aspect of human civilization and global politics. Agencies may fear that publicly acknowledging they are considering artificial origin could trigger premature public reactions or could undermine confidence in agency expertise if the hypothesis later proves incorrect. A third possibility, perhaps most concerning, is that detailed analysis is occurring within classified channels rather than through open scientific process, with results being withheld from public disclosure for national security reasons. If there is serious possibility that 3I Atlas represents alien probe, governments might classify investigations to control information flow and to prevent adversary nations from gaining strategic advantages if technology could be recovered or understood. The absence of public discussion might not reflect absence of internal investigation, but rather decision to conduct that investigation secretly. Regardless of which factors dominate, the result is inadequate public communication about observations that should be generating intense open scientific debate. The data are publicly accessible. Multiple independent researchers have analysed images from Hubble and ground-based facilities, deriving consistent measurements of jet properties, rotation rates, geometric configurations, all supporting the anomaly catalogue we have discussed. These findings should be prominently featured in NASA briefings and press releases. They should be driving expanded observation programs and generating proposals for potential follow-up missions. Instead, we have silence from institutions while independent researchers, like Harvard professor Avi Loeb, work to bring attention to findings that establishment seems reluctant to discuss. Professor Loeb has been particularly vocal about the artificial hypothesis, arguing in papers and public presentations that the accumulated evidence justifies serious consideration of technological origin, despite the profound implications such conclusion would carry. His position has generated significant criticism from some quarters of the astronomical community, with critics accusing him of sensationalism or of lowering evidentiary standards by entertaining exotic explanations before exhausting all natural possibilities. These criticisms reflect legitimate concerns about maintaining scientific rigor, but they also reveal discomfort with conclusions that challenge paradigms and with publicly discussing hypotheses that might prove wrong. But science advances precisely by proposing hypotheses, testing them against observations, and honestly acknowledging when data supports conclusions that initially seemed unlikely. Loeb's willingness to articulate the artificial hypothesis publicly, to show how it explains observations more parsimoniously than natural explanations requiring stacked coincidences, performs crucial service by ensuring that this possibility is evaluated rather than dismissed by unstated institutional consensus. Whether he proves ultimately correct or incorrect, his advocacy for examining all viable hypotheses, including uncomfortable ones, exemplifies scientific method operating as it should. The spacecraft comments that Loeb has made, the suggestions that technical civilization might have reasons to align gas outflows from thrusters in the direction of the Sun, are not wild speculation but reasoned analysis of what functional requirements would drive design choices for interstellar probe. As we discussed in earlier analysis, maintaining sun-pointing orientation provides advantages for thermal management, for power generation if solar panels are employed, for communications if directed beaming is used, for trajectory control if solar thermal propulsion converts stellar radiation into thrust by heating and expelling propellant. Every one of these functional requirements that spacecraft design would naturally satisfy maps directly onto anomalous behaviors we observe in 3I Atlas: the pole-sun alignment, the sequential activation of antipodal sources, the sustained collimated jet emission, the stable orientation despite weak gyroscopic stability. All these features make sense if viewing the object as engineered system rather than as passive natural body responding randomly to solar heating and gravitational forces. This does not constitute proof of artificiality, but it demonstrates that artificial hypothesis is not just wild speculation, but viable model that should be evaluated alongside natural alternatives. Loeb has been careful to emphasize that we lack definitive proof, that high-resolution imagery showing geometric structure, or detection of radio transmissions or measurement of unusual chemical composition would be necessary to conclusively establish artificial origin. But he argues correctly that absence of smoking gun evidence does not mean we should ignore the circumstantial evidence that is accumulating, that the probability analysis demands we take the possibility seriously rather than dismissing it reflexively, because it challenges our assumptions about uniqueness of human technology. The criticism Loeb has received, the accusations that he is lowering scientific standards or seeking publicity by promoting exotic explanations, reflects deeper tensions within the scientific community about how to handle observations that do not fit comfortably within established frameworks. Some researchers believe the appropriate response is extreme conservatism, exhausting every conceivable natural explanation, no matter how contrived, before even mentioning artificial possibility. Others, including Loeb, argue that when natural explanations require numerous low-probability coincidences, intellectual honesty demands considering whether alternative frameworks might better explain observations even if those alternatives carry uncomfortable implications. This debate is not just about 3I Atlas, it reflects fundamental questions about how science should operate when confronting potentially revolutionary observations. Do we prioritize avoiding false positives, ensuring we never prematurely claim extraordinary discoveries that later prove wrong? Or do we prioritize avoiding false negatives, ensuring we do not miss genuine discoveries because they seem too extraordinary to seriously investigate? Different researchers weigh these risks differently, leading to legitimate disagreements about appropriate evidential standards. My position, which I have tried to articulate clearly throughout this coverage, is that the accumulated evidence warrants serious investigation of artificial hypothesis alongside natural alternatives, that the probability arguments are strong enough that dismissing artificial possibility without careful examination would constitute intellectual failure rather than scientific rigor. But I also acknowledge that definitive conclusions require better data than we currently possess, and that December 19th closest approach provides crucial opportunity to gather observations that could discriminate between competing explanations. What should we be looking for during December 19th observations? What measurements could strengthen or weaken the artificial hypothesis? Several key diagnostics emerge from our analysis. First, high-resolution imaging attempting to resolve the nuclear surface structure could reveal whether the body shows the irregular, cratered, heterogeneous appearance typical of natural comets, or whether it displays unusual geometric regularity or artificial-looking features. Current images show only unresolved point source surrounded by coma, preventing assessment of surface morphology. Second, spectroscopic observations of the jet composition could detect anomalous chemical species or unusual abundance patterns inconsistent with natural cometary material. If the jet contains refined metals, synthetic organics, or isotopic signatures of nuclear processes, that would provide strong evidence for artificiality. Conversely, if composition matches typical cometary volatiles without unusual enrichments, That would support natural interpretation even if behavioral anomalies remain unexplained. Third, precise astrometric measurements tracking position with millisecond accuracy could detect trajectory modifications indicative of active maneuvering. If the object executes discrete thrust events that change velocity in ways not explained by continuous outgassing responding to solar heating, that would suggest active control. If trajectory remains smooth following gravitational plus expected outgassing forces, that supports passive dynamics. Fourth, radio observations searching for electromagnetic emissions beyond the thermal radiation any object naturally produces could detect transmissions indicating active electronics or communication systems. Extensive SETI monitoring has been conducted without definitive detections, but December 19th geometry might allow better sensitivity, or might occur during transmission windows that were inactive during previous observations. Fifth, detailed photometric monitoring tracking, brightness variations with high temporal resolution could detect periodic signals too rapid or too regular to be explained by simple rotation, potentially indicating mechanical systems or power fluctuations from active electronics. Natural bodies show brightness variations from rotation and from evolving activity levels, but artificial objects might show more structured periodicity or correlation between different observable features. The reality is that even with optimal observations during December 19th window, we may not obtain definitive answers. Resolving kilometre-scale nucleus at distance of 1.88 AU requires angular resolution of about 0.1 arc-second, at the limit of what Hubble Space Telescope can achieve and far beyond capability of ground-based telescopes unless atmospheric conditions are extraordinary and adaptive optic systems perform perfectly. Spectroscopic observations with sufficient resolution and sensitivity to detect trace anomalous species require long integration times that may not be available during the brief optimal viewing window. Most likely outcome is that observations will provide improved constraints on nucleus properties, better measurements of jet characteristics, refined trajectory information, all valuable for advancing understanding but not necessarily constituting smoking gun proof of either natural or artificial origin. We will emerge from December 19th with better data but possibly still in regime of competing hypotheses, with probability arguments refined but not definitively resolved. If that is the outcome, if we remain in uncertainty despite improved observations, then what conclusions should we draw? How should we proceed with investigation of 3I Atlas, and with preparation for future interstellar visitors that may exhibit similar anomalies? Several recommendations emerge from the analysis we have conducted. First, data should be openly shared, enabling independent verification and diverse analysis approaches. The history of science demonstrates that breakthrough insights often come from outside mainstream institutions, from researchers bringing different perspectives or different technical backgrounds to problems that establishment has struggled with. Restricting data access to small groups or classifying information limits the intellectual resources that can be brought to bear on interpretation. Second, institutional caution about discussing uncomfortable possibilities should be balanced against public right to participate in fundamental questions about cosmic context and potential contact with other civilizations. Space exploration is conducted with public resources and generates findings that affect collective human understanding of our place in the universe. The public deserves honest discussion of observations and hypotheses, even when conclusions remain uncertain and even when implications are profound. Third, additional resources should be allocated to enhancing detection and characterization capabilities for future interstellar objects. If 3I Atlas represents artificial probe, others likely exist and may pass through our system in coming decades as astronomical survey capabilities improve. If 3I Atlas is natural but exhibiting novel phenomena we have not previously recognized, understanding those phenomena requires better observations of similar objects. Either way, investment in improved detection and characterization delivers valuable return. Fourth, serious consideration should be given to potential interceptor missions that could rendezvous with 3I Atlas before it recedes beyond practical range, or that could be positioned to quickly reach future interstellar visitors discovered at earlier stages when longer observation windows are available. The technical challenges are substantial, but not insurmountable with current propulsion technologies, especially if we accept one-way missions that image and analyze the object during flyby without requiring return to Earth. As we stand hours from December 19th closest approach, as facilities worldwide prepare coordinated observations, as researchers ready analysis pipelines to process torrents of incoming data, I want to directly address you, the audience that has followed this investigation through its complexities and uncertainties. Your engagement matters, your attention validates the importance of these questions, and it creates accountability for institutions to conduct investigations openly and honestly. If you found value in this detailed analysis, if the careful examination of probabilities and observations and implications has helped you understand why 3i Atlas represents potentially historic discovery, then share this content widely. Most people remain unaware that these observations exist, that we may be witnessing something without precedent in human history. Mainstream media has largely ignored the story, or has treated it superficially, without engaging with the profound mysteries that detailed analysis reveals. You can help expand awareness, ensuring that important discoveries receive attention they deserve, rather than being lost because they do not fit convenient narratives. Comment with your assessment. After reviewing all the evidence, after considering the probability arguments, do you think 3i Atlas is extremely unusual natural comet exhibiting 1 in 40,000 geometric coincidence, plus additional improbable features? Or do you think the artificial hypothesis better explains observations through unified framework of intentional design? There is no wrong answer here. Reasonable people examining same evidence may reach different conclusions based on different assessments of prior probabilities and different weighing of how many coincidences we should accept before considering alternatives. Subscribe to this channel and enable notifications because the story continues beyond December 19th. Analysis of the data collected during closest approach will occupy researchers for weeks. Additional observations will track the object as it recedes, monitoring how properties evolve with distance and time. Debates about interpretation will intensify as constraints tighten, and as probability arguments are refined with better information. I will be here covering every development, maintaining the detailed technical analysis that has characterized this coverage from the beginning. Whatever we learn from 3i Atlas, whether it proves to be extraordinary natural phenomenon forcing us to expand understanding of cometary diversity, or whether it proves to be first confirmed detection of extraterrestrial technology demonstrating that intelligence and engineering extend beyond humanity, the discovery teaches us about reality beyond our immediate experience. It expands horizons, it challenges assumptions, it forces us to confront questions about prevalence of intelligence, about goals that motivate exploration, about whether the galaxy contains civilizations older and more capable than our own, that have been sending probes for eons while we were still confined to single planet, unaware that universe was full of complexity we had barely begun to imagine. We are privileged to live in an era when technology allows us to detect and study these visitors, when telescopes can resolve structure and composition of objects from other stellar systems, when analysis techniques can extract information from images and spectra that reveals physical properties with precision that would have been impossible just decades ago. This capability brings responsibility to use it honestly, to follow evidence wherever it leads, to resist both the temptation to sensationalize and the temptation to dismiss, maintaining rigorous evaluation while staying open to possibilities that initially seem unlikely, but that accumulating data increasingly supports. The December 19th observations will come and go. The object will recede, eventually leaving our detection range, continuing its journey back into interstellar space where it will travel for millions of years before potentially encountering another stellar system. But the questions it has raised, the challenges it has presented to our frameworks and assumptions, those will persist. They will drive research programs, fuel debates, motivate improved observational capabilities, shape how we think about cosmic context and about humanity's place in the universe, that may be far more populated and far more complex than we have previously imagined. Thank you for engaging with this investigation at the level of detail and rigor it deserves. Thank you for being willing to confront uncomfortable possibilities rather than demanding premature certainty. Thank you for participating in collective human effort to understand this mysterious visitor and what it tells us about what exists in the vast spaces between stars, about what travels through those spaces carrying what messages or what purposes, and about whether we have been alone all this time or whether intelligence and technology are common features of cosmic evolution that we're only now beginning to recognize as our capabilities grow sufficient to detect the signatures they leave when passing through our cosmic neighborhood. Like this content if it provided value. Share it so others can participate in this historic investigation. Comment with your analysis and conclusions. Subscribe for continued coverage as the story develops beyond December 19th, and keep looking up, keep questioning, keep demanding honest engagement with observations that challenge paradigms, because that is how science advances, that is how understanding grows, and that is how humanity will ultimately comprehend its cosmic context and determine whether we are truly alone or whether the universe is full of intelligence waiting to be discovered by those brave enough to look and humble enough to acknowledge when evidence points toward possibilities we did not anticipate and were not prepared to accept, but that reality insists of viable explanations for phenomena we observe when we examine them honestly without prejudging what conclusions are comfortable versus what conclusions are actually supported by accumulating weight of data.